So what is the downstream task in using the graph neural network? So this is the most popular one. We give the input graph data. As I said in the beginning, all the V and E's are available before the learning. We try to predict the gray node, labels of the gray node, but we already know the other colored node and try to predict their labels in the prediction stage, in the testing stage. So in the GCN paper, they using 4 different data sets. So they all the types of the networks are citation network and knowledge graph network. So they have their own number of knowledge nodes and edges and classes and features and the labels late. Label late means how many the nodes are labeled for the training. So considering 3.6, so this is 3.6%. This is pretty low percentage, right? So assume that when we multiply, so 3 times 27 and get some value, right? But this is very small, and just 3.6% is labeled for the training. So that's why this task is very hard. And when we see the Cora data set and citation data set, so it was in here, right, in a second. So this is the smallest one. So they are taking feature matrix, so which is composed of the bag of words feature vector. So assume that I'm not sure about their actual dimensionality. So we can construct a vocabulary matrix. Let's say that's F. F is composed of the bag is composed of the, for example, the deep and learning. And these words are included in the bag. Let's say this is composed of 3,000 features. So I'm not sure about their feature vector, so please check it out. And depending on the paper, some paper include the deep and some paper that does not include the deep. Depending on the appearance of the feature, they have something like this feature vector, and that will be used for the feature matrix X, and the edge between the paper is undirected, and it is from the citation data set. So result of the graph neural network from the Cora, where we visualize the result using TSNE, and you are able to get these visualization. It's quite identified well. So the color represents the conference domain. It is from the physics paper, it is computer science paper, or some system paper, something like that. They are well identified. And when you see the summary, so compared to the previous work, they also compare the debug, but different from the debug. Debug is unsupervised approach, right? They get the representation from the skitgram. The skitgram is unsupervised approach, and then trained logistic regression for the node classification later. Anyway, it got better result in the classification task. So it is quite promising result, and their actual time complexity is also very low. So when we get the time complexity, we are getting this. It is the multiplication of the number of edges and number of features from the class label. It is from our GCN layer. So assume that we have the two layers. We get the H, X, W, and ReLU, and then we also A, W, and ReLU. And the propagation corresponds to the number of edges, right? I told you these multiplication could be seen as a propagation, right? It corresponds to the number of edges, and this multiplication is also heavily depends on number of feature input, number of features, and final multiplication depends on the number of class labels. So the other constants in this computation is ignored to get the time complexity. So anyway, these are usually small. These are usually small and constant. So we are able to say it is linear to number of edges and quite efficient, and still we're getting a very good widget. And this is a very good, particularly where we have the small percent of the labeled node. When you use 10% and 20%, 30%, something like that, the others are also very good. And in practice, they are not they're not much different. But when you have small number of labeled node, then GCN works better. Alright, so I told you the multiplication between the adjacent normalized adjacency and the feature matrix is the propagation. And this is the GCN paper's suggestion, right? Beta is the trainable parameter, so it was previously W. But we can consider other variants, right? We just ignore the adjacency. We just directly utilize their own feature information. Or without adding the self node, we just propagate the neighboring nodes information. Or we use the single parameter, so the self edge is added later, or you can use another first order model like this. So, but empirically it returned the better result, particularly the most the largest data set. It is getting better result. So the paper is making the theoretical connection between the GCN and the spectral filter and spectral neural network. So previously we had the input of GCN like this, and this is derived from the normalized Laplacian actually. So in the original normalized Laplacian is computed like this. For this, D is a degree matrix and A is adjacency. We define the L is D minus A, and we normalize their degree information, and we get the final normalized Laplacian matrix. So in the previous spectral methods on the graph data, they have used for this normalized Laplacian for their own downstream tasks such as clustering and node classification, link prediction, something like that, because it has many useful properties. So, such as the smallest eigenvalue is always 0, And second smallest eigenvalue tells you about the connectivity of the input graph. So if the graph has two connected components, two disconnected components, and the second smallest eigenvalue is equal to 0, if the second smallest eigenvalue is small, this suggests that this graph is nearly disconnected, and many more properties they have. So from the input, the normalized Laplacian matrix, so this is the eigenvector from the second and third and fourth and eighth eigenvectors. So the input graph is from the human behavior based graph data. So this is colored from the value of the eigenvalue. So which means I'm eigenvector. So this is a U2's eigenvector space. So we have some float value in this axis, right? This is U3's eigenvector axis, and this axis. So depending on the float value, when they have the large eigenvector in this space, we give the blue, and the opposite is the red. And when we backtrack the actual node in the human body, so we are able to identify the head and the middle part and the bottom part from using the second eigenvector. What about U3? It is identify the left and right foot, right? The fourth eigenvector is able to identify left hand and right hand. U8 is identify this part, right? The knee. So the Laplacian matrix is very useful for the human body detection. So this is one of the use cases from the normalized graph, and many people have used the graph data a lot for the motion detection and clustering tasks. So using the information, so from the original, the eigen decomposition of the graph data, and we can develop the simple graph filter based convolution approach. So the input graph could be decomposed using the SVD decomposition, right? And from the L could be decomposed into U and lambda in UT. This is from the SVD, right? And we can give the filter function to this function. So we try to consider what kind of the graph property is important. So it depends input, right? Even though we are able to identify the meanings of this axis, sometimes you are more interested in the detect the head. Sometimes your class labels are more related to the left and right foot, right? So we have to determine which eigenvector is more important for your task, right? It controls by using the splitter. The splitter decides what eigenvector is more important and how to use for your actual prediction. So some very simple mathematical derivation. So G could be put in between the U and U. So which means it is actually the function of eigenvalue. So this is also the very fundamental form of the spectral graph convolution layer. So which is same as the training eigenvalue filter. But to learn this layer, we always have to have this eigen decomposition. So this is a very computationally heavy task. So to avoid that, people developed a more efficient approach, which is called Chebyshev Expansion. So the computational complexity corresponds to number of edges, big of the number of edges, and we are able to substitute this part to here, and their actual computation is from the summation of the k number of these terms. So each term is computed from this. So the each TP computed from the previous two terms, and first is determined from the x and lx. So with this way, we can approximate this one. Yeah, it's actually saying, so this is I'm sorry, right, and we just use this information and we get the final prediction. So I would say in this approach, we don't compute the U and eigenvalue, full eigenvector eigenvalue matrix. And considering this, they are able to get the eigenvalue filter information. So for details, please refer to this paper. And so when you see the result, and they're still better compared to this, right? Oh yeah, this is, I mean, GCN is better compared to the previous one. So, but they have the theoretical relationship, and in PubMed it has better result, but the others are not much different each other. So from the GCN, we can notice that the graph neural network problem is the sort of the design choice of the neighborhood, the propagation function, and nonlinear activation function. So let me give you the details. So more generalized version of GCN. So we slightly generalize from the original GCN. So previously we get the neighborhood function is from the adjacency, right? So we, instead of the adjacency, we get the neighborhood function in here. So it depends on your own definition. So your neighborhood is from the connected neighbor, or your neighborhood could be from your random walk, right? It depends your network, the properties, and your own decisions. And from the neighborhood function, you get your neighbor, and you summate the current features and normalize based on the number of the neighbors, and then multiply the W. This is a trainable matrix, and you can consider the embedding self information, and we can also transform the self information in another trainable neural network, and you can choose your own activation function, and then you get your own embedding. So this is a slightly generalized version of the GCN, and another version of the generalized GCN is presented in this paper, and this is part of your reading assignment this week. So you aggregate the neighboring nodes. This is from the neighboring function I told you. So it could be from the connected nodes or random walk, something like that. Sorry. And aggregate, and you can combine from the self node, right? So we get the aggregated representation from the neighbors. So this is from the propagation. The weighted sum, the summing over the neighboring features or neighboring representation, is called the aggregation. So propagation or aggregation, they all presenting the same meaning. And combine the self representation, and you get the final representation of the layer. So GCN is this case. It is like the weighted sum. Weighted sum could be presented using this, could be said as the mean, right? Because it is weighted using the normalized adjacency. So in that sense, you can call this as mean, right? And ReLU and W, and it is GCN. Another graph convolution, graph neural network paper, the graph stage. So one of the approaches is use the max pooling. So instead of the activating all the values, so we use the max pooling, and we use the most significant signals to decide the representation of the node. So it is like a design choice for your own model. It depends your graph. Your graph is from the natural language dependency tree or computer vision, the pixel or segmentation trees. It depends. You have to choose your own the aggregation and combine methodology. So to train GNN, so we reduce their dimensionality in the supervised setting. Maybe at the final layer, the output shape, the output dimensionality could be the same as the number of class labels. And we put the softmax layer here, and we get the final prediction from the function f, and we compare the true label, and we compute the cross entropy between the two vectors, and we train neural network. So it is like a usual supervised learning methods. So for GCN paper, they use a batch learning, not a mini batch or stochastic gradient descent based learning. They use batch learning. So when your graph is heavy, and when you use many number of the node set, and it will be very computationally very heavy. And on supervised setting, so by going through the GCN layer, you have your own representation, right? U and V. When they are connected, and their similarity should be higher than the other node, right? So you have to decide similarity function using the decoder. So decoder could be anything. So you have we have dealt with the decoder function in the network embedding, right? Using the inner product, something like that. And we use the cross entropy, or we can use negative sampling. Exactly same as the network embedding. So we have our own representation from GCN. We can use the same loss function as in the network embedding approaches. So decoder could be anything. So this is the example. And how would you apply this GNN for inductive setting? So for the unseen nodes. So we can still utilize the trained parameter W and B, right? So empirically, it is also known that it is a very good, it shows a very good performance in the inductive setting as well. So for example, the graph classification, it shows significantly better accuracy compared to the previous baselines. So because the graph data, we assume that even though they are entirely different graph, the population is from the same the distribution, and we believe that the neighboring nodes are distributed in the similar ways, and we still apply the trained parameter for the unseen node. All right, this is the end of today's lecture. So this is a reading assignment. So read this paper and submit your review. So this is the reading assignment. So you have to submit some good things about paper from your own opinion. So make a one paragraph to describe good things, but don't include any sentence from the paper. Don't copy and paste. I will check it out. All sentences should be from the scratch, from your words. Don't copy. So find the good things, make a paragraph. And your opinion to improve this paper with the one paragraph. How would you improve this paper? Maybe you may include some future work and some missing points, or with disadvantage, and so on, and anything could be fine. So any questions, let me know. Thank you for your attention and have a wonderful weekend, and bye bye.